All right, it's time. Let's begin. This is episode 6, the second lecture of week 3. To begin with, I would like to remind you, the quiz number 3 and 4 are due this Friday, tomorrow, 6 p.m. Second is the PA2 is also due tomorrow, 6 p.m. So if you haven't done so, try if you can beat the buzzer this time. And the second point I would like to communicate is this. I realized that the videos I've recorded for the PAs, they could go really long. So it ended up they might be longer than what I need to make up for the 2 weeks that we are skipping, the week 17 and the 18th. And some of these PAs are a bit critical, starting from PA3 particularly, because you're beginning to do the circuit programming. It's not exactly harder, but it gets slightly trickier, and it could be confusing sometimes. So I want to make sure that you guys walk through the videos, and having an opportunity to ask questions and interact with Polly. So what I will do is that for the next few weeks, the second hour of the Thursday's lecture is going to be more about the PAs. So I'm going to play the videos I've pre-recorded and in the meantime allowing you guys to ask questions in the middle of it. So this is the second point. And the third point I would like to communicate is this. Also, I would like to dedicate some 5 to 10 minutes of time to go through the questions and answers in the live chat. I actually think about yesterday's live chat a little bit. There are quite of you guys trying to interact, but I kind of ignore some of them because I already answered the question. But the thing is that I was answering the question in the middle of playing out videos. And those live chats, interactions are not recorded in the video. But during the playing of the lectures, I think it's a bit hard to also place the live chat screens on the side. So what I will do is at the end of the lecture, I'm going to leave 5 to 10 minutes just to walk through the entire live chat, okay, just so that I don't miss anything, and I don't miss anything that you show off your question asking skills or commenting skills. So, good. So that's the third point I would like to communicate. So now back to the lecture. Yesterday we were talking about circuit. Because internet applications or network applications, there are oftentimes multiple processes on multiple end systems. So these processes are communicating through sockets. So we try to explain what socket means and why it's called socket in the internet. Next, we'll see where is the socket implemented in the operating system. So let's continue playing the video, but I'm gonna roll back just a little bit and starting from socket, and that's coming now up right now. Now more about the processes. Network processes will be sending messages to each other and through this thing, socket. So you might be thinking, why socket? Why is this term keeps popping up? Right? Yep. You can think of it this way. How do we call this thing? Right? This is the eye socket. What does that mean? Okay, that is the entry point of lights. We have power socket. What is power socket for? It's where you plug in, right? The power plug. So here, socket or network socket is where you push messages through, okay? Or you take messages out. So that is why we call this thing network socket. All right, so it's sort of a gateway of messages. Good. So socket here, another analogy is, yeah, it's almost like the doorway. We send messages over the door. Okay, so sending process shoves messages out the door. The sending process also rely on the transport layer service that's right underneath to deliver whatever the message that we shove out of the door. All right, so again, we see transport infrastructure. So application here only handles passing the message through the socket. Application there sometimes does not do too much controlling the speed of sending these messages out. More often, we have the transport layer service here to support adjusting the sending rates of these messages. All right, so in the figure below, we see application layer process sitting at the application layer. So one is sender, one is receiver. Messages go through the socket, being shoved through the socket, and it goes through the internet and reaching the other way. So this socket here grabs the message and passes it up to the process. And that's how the receiver gets the message. Right? For different languages, you see different APIs to do sending, receiving. In Golang, you will see that the very basic one is simply read, okay, for the receiver. The basic one for sending is simply write for the sender. There will be a lot more in the PA assignments. Now, the last point, the protocol stack, from the physical layer all the way up to the transport layer. These are all controlled by the operating system. Once you have installed Windows, once you have installed Mac OS or Unix, Ubuntu or Linux, whichever you like, you've already installed the entire suite, okay, of the protocol up to the transport layer. Now, the application layer protocol, however, is controlled by the application developers. All right. So once you set up your laptop, yeah, nowadays it came with the web browser, IE or Safari. But IE and Safari, if you look at it, it's actually also a separate application. You can actually remove it, and still your operating system can still operate. So, World Wide Web, the protocol that's implemented in the web browser is controlled by the app developer. It comes with the app. Okay, so separation of the application layer protocol and the other protocols. Other protocols in the operating system. Application layer protocols are part of the apps that you're downloading. Now, to identify processes uniquely, now think this way. To receive a message, you need to really have an identifier so that the messages will go to the rightful process. There could be multiple processes running on a host. If we are only sending the messages to the host's IP address only, then how does the host know that, hey, which process, right, the message is for? Okay, so question, does IP address of the host sufficient for identifying the process? Well, hey, you guys are thinking this, obviously. No, right, there could be multiple processes running on the host. So the identifier definitely needs to have the IP address so that the message goes to the right host. But that's not the only component. It needs to be in the identifier. We also need a special number. In this case, the port number. Okay. On the internet, we call this address to identify individual process on the machine, the port number. So, to identify a process, it's a combination of IP address plus the port numbers. So an example port number for some of the well-known processes. So if you run a very powerful machine and you could implement or install an HTTP server, which is also the web server. Now web server is given a default port number 80. Mail server, port number 25. SSH, I think it's 21 or something like that. Okay. So there are well-known services in the world, HTTP, mail, remote logging, that operates on the well-known port numbers. Right? So to send HTTP messages to, for example, this web server, this is the IP address of gaia.umass.edu, and because web server is oftentimes just running on the default port 80. So to send a rep request, you take this combination, and that's going to identify the web server processes running on Gaia. Right? So there's going to be more later on in chapter 2. Let's take a pause here just to check whether pollys recording is going well. Well, turned out that we have enough time to cover this. The application layer protocol. What's defined in a protocol like this? First thing, well, application layer protocols are essentially exchanging messages between the processes. So we need to define type of messages that we exchange. Now, you see earlier, I often use the web as an example. So we send web requests. As a result, the server sends back the web response. So there are two types of messages. Now, depending on how complicated your application layer protocol is, there could be more than two types of messages. And then we need to define the syntax of these messages. For example, web response might say, okay, everything is fine, 101. Okay. And sometimes it says, oh, something is wrong, 403. Yeah, some of you might have seen messages like that saying, hey, yeah, page not found, 404. Okay, so those are message syntax. So there are special things or fields in the messages that's telling the client what's going on at the server. What is the service being requested? Is it okay? Am I providing the services? And what time I'm providing the service? And when is the service last available? And when is the last time you have requested the services? So there are all sorts of things these messages might be defining and indicating the status of the exchange. All right. So oftentimes multiple fields, not just the type of message, not just the specific status of the service, but also time, operating system of the server, etc. And then, hey, I use 404 as an example. What does that mean? Yeah, in the protocol, what's also defined is that for these code words, they are often short for communication purpose, but behind each number, behind each special term, there might be quite a set of semantics. So meaning of information in these fields. And then, last but not the least, the rules about exchanging the messages. The server process might be sending back a response after it receives a request. But some applications, such as P2P, these exchanges of messages can be a lot more complicated. So typically in an application layer protocol, you see, we need to define how many messages and define the types. Define fields in each of these messages so that they can provide important information to the other side. And for engineers like us to understand, what is the meaning of these special code words, special keywords, and then the flow of how these messages gets exchanged. Right? Now these protocols can be categorized based on whether all these rules, definitions are provided open to the public or private, so it's more secretive. Some of these popular applications we know are open. So there's this document, RFC, request for comment. Each protocol has one of these RFCs. Some protocols, more complicated, will have multiple RFCs. If you look up one of these RFCs and read the content, you'll see, wow, there's a lot of details one needs to put in, a lot of effort there in order for one to implement, for example, a web browser such that it will interoperate with any web servers on the internet. So web servers can have different implementations, just like web browsers can have different implementations. We have Safaris, Chrome, Firefox, etc., etc. Each of these web browsers need to be able to work with each of the existing web servers, Apache, Nginx, etc. All right. Now, you see, web HTTP is one such open protocol. Therefore, we see a variety of these processes that we could download and install. Email also, right? Email readers, nowadays there are many different forms. One can also download free email server as well as proprietary email servers. Now, the email readers and all these email servers will need to be able to interoperate. With protocols being open, we could have a variety of them working together. So what's nice about this is such that, hey, better programmers, better teams show up, they could actually improve the performances of the servers or the clients. Therefore, we get faster web services, faster email services. Now, proprietary protocol, yeah, it's all secretive. You can't find any definition of it. But sometimes hackers who are a bit bored may try to hack. I think some 10 years ago when Skype just showed up, because it was super hot, because it worked quite amazingly. People worldwide can just call each other for free. So there were some hackers trying to sort of backward engineer Skype's client, and therefore they could implement some other clients, allowing other people to call up using Skype. That was a very ambitious project. I've tried it. It kind of worked. But Skype learned about that hacked client and then quickly changed something, and that hacked version stopped working. So that's what's wrong with the secretive protocol. But that's also right about that's also what's nice about the secretive protocols, because then it will fend away all the competitors. Okay, so until today, Skype is still Skype. There's only one Skype program that you download. But we do have other forms of competitions. Nowadays, we download Line. We could also download Google Hangout. Yeah, but your friends will have to, switch to these other platforms. Good. So that's going to be all for this week. I'm just going to stop the video right here. Excuse your stay, and let's come back here. We're at a transport layer service, and that is flashback a little bit. So we're now trying to design the network application. Okay, we've discussed you need to first decide what is the architecture. Okay, is it server client? Is it peer-peer? And then you want to think about what language you want to use to program the app. And you learn that the processes running on the end systems will be transferring messages through this thing called socket. So after the socket, the messages will be going to the operating system. And at the top of the operating system is what? The transport layer. And that is the thing we need to decide here. There are multiple choices. Which one do you pick? Yeah, it depends on this thing. The nature of the application you're trying to design. So that includes the content types. Are you transmitting text? Are you transmitting audio video? Are you transmitting game data? It also depends on the use. Okay. Is it more interactive or not interactive at all? It also depends on the user expectation. Yeah, sometimes the users are more used to, quick service, a very high volume service, they might be demanding more, right? So, to what level quality you want to provide your applications? Those are called the quality of service. The first is called the data integrity in the textbook, but what the authors of the textbook meant is reliability. Okay. So the text content here is the one that's particularly interesting and requiring 100% reliability. This type of content is very vulnerable to loss. Let me give you an example. Let's say you want to send a message back to the home universities, telling your friends that, hey, NTU is a really cool university. So you say NTU rocks. But if you're choosing a service, transport layer service that's not reliable, then hey, let's say these two characters got lost. Then this is subject to interpretation, isn't it? Yeah, your friend there might be mistaken that as NTU sucks. That would be the exact opposite of what you meant to say. Well, not to mention, hey, it actually looks similar to the F words, isn't it? So that is just to show you that text-based content, most of the time, we just set it to 100% reliability. So we pick a service that provides 100% reliability. Now, audio video, particularly audio video streams, then can tolerate to losses. As you're transmitting a stream of audio or video, if we lost a segment in the middle, if it's short enough, what human brains can do is to try to fill the gap in with the context before and after the loss. So those apps can potentially be loss tolerant. And the next service requirement that people often talk about is timing. This is better known as this, delay. Most of the applications does not require strict delay, but this type of application does require low delay. The interactive applications, so internet, telephony, as well as shooting games. First-person shooting games, particularly, are very interactive. And those applications require very short delay. The delay needs to be lower than 100 milliseconds in order to make sure that the receiver of a message or a receiver of audio stream to think that you're saying it right now. And so they can talk back quickly. They can fire back quickly, all right? Those with high reflex might argue, hey, the delay needs to be lower than this. Yeah, as I said, right, first-person shooting game. Someone with really, really good reflexive, they can tell. They can react real quick, all right? So timing requirement, delay, so to speak. Third is throughput. I think a better way to call this is bandwidth. Okay, can we provide certain amount of bandwidth to transmit the content? The network bandwidth in particular. So some applications do require a good amount of network bandwidth in order for it to work effectively. So this is Yeah, streaming video. As you are watching here, a streamed video. What I'm trying to send out is this much, okay, 200 megabits per second. YouTube recommends a minimum of this much, 1 megabits per second. Now, if you're seeing the quality is already not that good, you see that 1 megabits is going to be worse. Now, anything lower than 1 megabits per second, you might not bother because the video quality is not so good, isn't it? Yeah. So you see also a little bit of the user expectation here, because we are pretty much spoiled. For a Ethernet fixed wire network, you definitely expect very high throughput, very high network bandwidth, and you're used to high quality video. So when it suddenly you move to 4G, then hey, that video might not be effective at all, not satisfying at all, right? But other than videos, most of the other applications are elastic, meaning there's no strict requirement that you want to guarantee a certain network bandwidth, right? So they will just make use of whatever throughput they get. Last, service requirement, security. Now this is actually something that's growingly important. In the 90s and the early 2000s, security was not even a service requirement at all. As at the time, people are yet to worry about providing better throughput, better timing services, better data integrity. Only these recent years, people are more aware about security issues, therefore begin to demand we provide enough security in the applications. And that includes two kinds of security. One is confidentiality. Are we encrypting data? Are we encrypting the messages so that people cannot hack what we're doing? The other type of security is this, data integrity. This is so that we can prevent any third party from spoofing our data and pretending to be the sender and send something that mislead us, okay? Falsified information. So all four together, service requirements, or also called the quality of service. So a big part of the network layer protocol design is to decide first, what is the quality of service that we're trying to provide, all right? So this part of the design is not technical. It's more that you need to think for your user. You need to think for the services such that the users using the application will be happy. Now let's go through some common apps and look through the service requirements for these apps. First app, file transfer. This is a very classic app as most of the files contain text. So here, no loss. Now the file transfers oftentimes does not require it being sent in a timely fashion, so no delay requirement. It's not time sensitive at all. As a result, there's no need of bandwidth guarantee. The bandwidth can be very, very low, but we are not expecting it arriving at a specific time anyway, so it's very elastic. So things like Dropbox, when you move a file into your Dropbox folder, you see that Dropbox there might be doing the uploading for days. As you know, most of our household network, the uplink bandwidth is very narrow. Okay? Now, similarly, you can probably project email, web documents being also text. Then we demand no loss, and there's no delay requirement. Therefore, there's no specific bandwidth requirement. Real-time audio video, however, very different. As we were talking just now, there are loss tolerant, right? Because if we miss just a short fragment, we could actually fill in ourselves. And for interactive audio video, what's even more interesting is that, hey, when we were speaking over internet phone service. If I miss something you say, I'll just say, hey, hello, you were breaking up last sentence. Could you repeat that? In a way, the human beings can serve as a reliable service on top of the internet, on top of your app. Okay. So, no loss, not that important. Instead, let's tolerate loss for audio-video apps. But, hey, real-time audio-video, we do demand a certain bandwidth guarantee. So, audio in particular demands lower. 5 kilobits per second should be sufficient, but anything lower than that is not really audible, perceivable. Video requirements is higher, 10 kilobits per second minimum, but the quality was really bad. Okay, it's probably okay for a real-time video conference so that you just see the facial expression. Well, sometimes with 10 kilobits per second, you don't see the subtle facial expression. Yeah, and these days, hey, spoiled users might be demanding this much. Very good quality video, very good quality audio. So I was just listening to an online concert from Berlin Philharmonic. Yeah, I would really prefer a higher bit rate for those audio streams, you see. And delay sensitivity, because they are real-time applications, very much sensitive to delay. And we want the delay to be lower than 100 milliseconds. Now, stored audio video is slightly different from real-time audio video. And it differs here. The tolerance of delay. It is delay sensitive. If you're watching Netflix, on a daily basis, you'll see. Although you do not require that it's real time, but you do want the video being played smoothly. As the network bandwidth fluctuates, you can only tolerate to a certain amount of these fluctuates. So what Netflix and YouTube, these type of stored audio video services, are doing is to, have a startup delay. So once you click into a Netflix video, you see that it's waiting, it's buffering. Yeah, for a few seconds. Yeah, that's the delay we were talking about here. Yes, it's delay sensitive, but it's not as sensitive as the real-time audio video streaming service. Right. Oh, by the way, it's delay sensitive. It's because, you don't want to wait for a minute, right, for the video to start playing. Next is the games. Most of the games are interactive. So you see, delay requirement back to yes and 100 milliseconds. Game data, the volume is much lower than the audio videos. So we need some guarantee, but it's very low. Maybe just a couple kilobits per second. And in some cases, the game data are loss tolerant. But recently, the games are growingly complex. You might want to think about this again. Older games, loss tolerance. But recent games or a new game that you'll be designing, you want to ponder real hard before you decide whether you use a reliable service or a non-reliable service. Last is text messaging. Well, you will not be surprised that, we see no loss here. And text messages, very brief, very short. It's unlike game. Game is actually a stream of short packets, a stream, continuous streams of game data. Okay, it's just that the game data is not as big as the audio video data. Now, text messages very short, even smaller than a file, email, or web. So, very elastic, no bandwidth requirement. Now, delay requirement. In text messaging, it's really getting complex also these days. In the older days, I don't know if you heard about this text messaging app called ICQ. ICQ. That's actually means I seek you. I'm looking for you. So in this app, when I was playing it the first time, I type up a message to my friend. I didn't get a reply in another day. So in the older days, people are not expecting very timely reply. But these days, people are using these texting apps so often, and many of us are using it in professional communication. Then real-time feedback is required, okay, in some cases. So that was common apps and the service requirements. Now we know about the QoS requirements of the app, we could begin to choose the transport layer service. There are two of them, TCP and UDP. The first one implements reliable transfer. This is the perfect for the text-based application, isn't it? What it does is that, hey, packets can still be lost in the network, but TCP implemented a mechanism such that it will try to resend and recover from the loss. So, guaranteeing reliable transport between sending and receiving processes. A second function it implements is this, flow control. This is to try to slow the sender down in case the receiver here is having trouble playing back the video, okay? Or the buffer space here at the receiver is already full, meaning the viewer there is probably hitting the pause and doing something else, and there's really no need of sending more video frames, okay? So flow control here is to adapt the rate the sender is sending out content, such that it does not overwhelm the receiver. Third is called congestion control. The purpose is this. The senders might be sending the data in an easy pace, but you see, congestions might occur in the middle of the network. And when that happens, packets get dropped. And the worst is that if there are more traffic coming in, you guys will just be competing for the network bandwidth or the buffer space really, really bad. And packet will get dropped more, right? Sending more doesn't really help because it just makes it worse. So in congestion control, it's also important that the sender here, okay, in TCP, try to slow down such that it's sending just the right amount of bit rate. Therefore, the network is not overloaded. So the technique is similar to what the sender of TCP is doing to slow down. In congestion control, if the network is congested, if the network is overwhelmed, we also slow down the sending process. And now, what comes next are the drawback of TCP. TCP does not provide any of these. It does not guarantee delay. It does not guarantee a minimum network bandwidth, and it does not guarantee that the data is going to be sent in a secure way. Another drawback is this. Before you can guarantee its reliable transfer, it's better controlled, the sender and the receiving process will need to establish a connection. So it's connection oriented. So there's a certain setup process, okay, before we can really send the messages. So yeah, there is a bit of startup delay, so to speak. And UDP service, it's the complete opposite of TCP. It's not reliable at all. Okay, so there's no retransmission to try to recover from losses. So it does not provide reliability. It does not try to control so that the receiver will not be overwhelmed. It will not try to control so the network will not be overwhelmed. It does not guarantee timing, throughput, security either, but it also does not have the connection setup delay. So this is probably the only good aspect of the UDP if you think about it. Now, why? Then why bother having UDP at all? Well, hey, you see, the advantage of UDP is this, right? So if you really want to send messages quickly, yeah, that's one reason you pick UDP. Another reason is this. If you recall back, now UDP is doing unreliable data transfer. Is there content that does not require reliability? Yes, there are. So for audio, video, or for real-time applications, the choice is often the UDP. Okay. All right, let's walk through a few applications and see what transport layer services they're using. First is email. Second, remote terminal access. So these are remote logging. So if you use PuTTY or use a Mac terminal to try to log into the workstation for the PAs, yeah, that's what the remote terminal access application is. So one could have multiple implementations of the remote logging service. And then World Wide Web, we know lots of web browsers. And file transfer, we have FileZilla as one example, and one can find many other file transfer clients. So each of these is an application. Now, most of the objects they're trying to transfer are text-based, so it's no surprise you see they use TCP. Now, the middle part here is just to tell you what application layer protocols you're using to support the operations of the applications. So SMTP here supports email. Telnet here supports remote logging. HTTP is the application layer protocol for web transfer. And FTP, capital F, capital P, capital P, T, capital P there is to support file transfer. Now, each protocol is defined as an open standard. So the document for it is RFC. So you see here a code for each of the protocols. So RFC 2616 is the document for web. Don't be surprised. If you Google it up, you see that there are 176 pages of it. Yeah, now some of you may begin to worry because in the second half of the semester, you'll be implementing a very simple web server. Yeah, and the reason that I'm saying that you are implementing a very simple web server is because of this exactly. Yeah, we cannot be implementing the complete web server. All right, so those are the easy applications, commonly used applications. We have two more commonly used applications. So this is streaming multimedia, such as YouTube. This is internet telephony, such as Skype. Now, they are audio video, so it's no surprise. Again, you see them using UDP as the underlying transport protocol. But some of them use TCP these days, and actually there are more and more of them using TCP, which I will describe in a little bit. So YouTube, for example, uses UDP as the underlying application layer protocol, such as web is doing. And because HTTP is using TCP as the underlying transport protocol, that means YouTube as a streaming service is using TCP as the transport layer service. Now, Skype as an internet telephony application, it actually uses both UDP first. So what it does is to try to call to the receiver using a UDP connection. In the earlier years, this has been working fine, but gradually the Skype engineers discovered that more and more of these call requests got blocked. So they never really get through. And they discovered that the reason is this. The antivirus softwares now we're using, they sometimes have a very interesting default firewall setting, which is to block UDP traffic entirely. And this is because many of the denial of service attack, because they want to not bother setting up TCP connections and just send a bunch of these UDP packets to flood a particular service. So lots of these antivirus softwares have this default firewall setting, blocking all UDP traffic. Now, because of that, when Skype discover a call initiation is blocked, meaning not responding, then Skype would turn to send the call request using TCP. And that's why UDP uses also just HTTP over TCP. This is because the firewalls never block port 80, which is the default port for World Wide Web, because hey, we will all at least need web access. All right. Complicated, isn't it? The reason that we're choosing a transport layer service ended up being more non-technical. Yeah, because there's security concern, therefore firewalls gets really strict over blocking things. Therefore, multimedia services will have to get around the problem using TCP and suffer from the problem that we have higher initial delay because we need to set up TCP connection. There's a call setup delay, a connection setup delay. Yeah, unfortunate, but that's the way it is. And next is quiz. All right, so we're back live. Yeah, quiz. And it's about time to take a break, so let's walk through the quiz real quick. And then you guys can actually think about this over the break. And when we come back from the break, we'll see what you have to say. And in the meantime, go through the questions in the first hour. Okay, not many there, but I also noticed that there are some, errors in the video recordings. So let me go through the quiz. This is number 6, okay, the second of the week. So here it goes. Should the game traffic be transmitted by TCP or UDP? Yeah, as I was talking about the QoS requirement for interactive games, right? I was saying that, hey, whether a game is really loss tolerant, it probably depends on the gameplay. You really need to think a bit harder to decide whether you use UDP or TCP. Or UDP with some extra mechanism in your application layer protocol. So think about these 3 games, okay? Think about these 3 games. First is the the Farmville. I don't know if you've played this game before. I did not play actually, but many of my friends were playing. So what it does is that you kind of farm, you plant vegetables or flowers or things like that. And over time, it will grow, and so the growing depends on how much care you're taking of your farm. And sometimes your friends or strangers may come to your farm and pick your vegetables without you noticing. So that kind of game, it's a web-based game, if I recall. What do you think? Would you use TCP or UDP for it? All right. So think. Do you need the data to be reliable? Is there a delay requirement? Is there a throughput requirement? So that is the first game. Second game is this, the pug. It's a first person shooting game. So it seems very critical because players are shooting each other all the time. So think whether is delay important, whether loss is tolerable. Okay, so which transport layer protocol would you use if you are designing a game like pub? And the third one, okay, so this one is called the multiplayer massive online role-playing game. So it's pretty long. So the game's name is RO, Ragnarok, or something like that. It's a bit hard to pronounce. Online, so Ragnarok Online. So there's a big story behind the game, and you kind of explore the world there, somewhat mid Earth or maybe some, outer space planet, and then there are some other people there. So there's a big story, and people are playing different roles, and there will be, players forming teams, groups, chatting with each other. But there will also be gameplays that you need to go out together to hunt. To, for example, identify mobs and beat them up, and then pick up treasure. So sometimes some of these mobs are really rare. These rare mobs, when you kill the mob, you get also rare treasure. So that is the kind of the gameplay. Okay, so some part of it being leisure, casual, you are probably chatting and doing some sort of game treasure shopping. But sometimes there are battles. It could be quite intensive. So what do you think? Should you be using TCP or UDP to transmit the data in RO? All right, so let's take a break for 10 minutes. And we'll come back in 10 minutes. So let me bring up the break screen. Okay. Sure. Please do. Yeah, Rocket, go ahead. All right, let's resume. PUBG? Oh, okay. Good to know. So you see that I'm not really a gamer, but yeah, at least I don't play PUBG. All right, so yeah, well, let's come back here. So let's first walk through, some of you post, I think just Rocket, right? Post quiz here. Good, so let's see. Quiz 6 from Team 1. So Rocket here is suggesting Farmville should probably be using TCP because latency is not really a concern, right? But you don't want to make sure that the data being transmitted is perfect. All right, good. And PUBG here. Team 1 thinks that UDP will be better because latency is pretty much everything in FPS. That's a good point. We don't want to load players' position from a few seconds ago. No. Otherwise, you could have been hit, but the person could have avoided as well. And if there were misses, let the pass in the past, So better pick up an AK-47 so you could shoot consecutively quickly. Yeah, I see. And RO, TCP. Yeah, the gameplay is a bit more casual, leisure, slower pace. And you do want to make sure those treasures are not lost. Yeah, the game rewards being transmitted reliably. Good. Yeah, so if any of the other teams or any of you guys think otherwise, please feel free to type up as well in the middle of it. There'll be some time in the later half, the second half, meaning the hour coming up, we can go through those input from you guys. Now, let me come back up a bit more here. Yeah, so when I was talking about processes are sitting on the servers, these server processes might be using some well-known ports because they are also well-known services. So I was saying that, hey, SSH is using port number 21. Web was using 80, things like that. But I was wrong. So SSH should be running on 22. Port 21 is for FTP, all right? And then, by the way, there are some code being defined to indicate the status of the web request. So the server sometimes says or returns a message to the client saying 404 not found, all right? So to be a bit more clear what I meant by syntax and semantics, so what I'm demonstrating here is exactly that. 404 is a code. So 404 is also part of the HTTP response syntax. So in the response, it needs to tell the client the status. So 404 is indicating a status. So the syntax there is that client and the server actually already agree on that, hey, the status is just going to be a code word, a number, all right? And the semantic is not going to be sent over the net. So it actually takes the documentation for both the client and server side to know what the code word means. So the web browser there will have to look up 404. Okay, it means that the object is not found. By the way, 403 there is also indicating something wrong, and it's indicating that the object download is prohibited. That is usually because the object's permission right is not set to globally readable. So this particular request will be rejected because of that. And Rocket was asking, this is a really big question. If you could design one aspect of the internet, okay, it could be protocol, organization, structure, what would you change? Or do you think that the internet protocol stack is already perfect? Well, you know what? It's far from perfect. And especially recently that I'm doing a lot more teleconferencing calls. And also doing this online lecture, I'm anxious all the time, worrying about the network bandwidth. Yeah, so you see here in the middle of the lecture earlier, yeah, the YouTube is actually telling me, error. The server, YouTube server, is not receiving enough video segments from me. And you guys might be experiencing sort of pauses or freezes. So yeah, I was very, very emotional during that period of time. But good thing is that the network was back doing well again. But hey, I would really rather that I don't have to worry. So I was saying here below, I think here, yeah. I would really like that a part of the internet can work like a circuit switch network, where the bandwidth is guaranteed. Really, I would rather pay for it and then be worry free. So that's what I want to change. That's where I want a change of the internet, right? So for online lectures, important teleconferencing calls, for some of you guys, game session. Yeah, because really, seriously, the way people are using the internet is really getting more serious and formal. And we're demanding more reliability and predictability of the internet, right? I don't know if you agree, but yeah, that's what I think the internet needs to change. And you know what? Internet is not entirely unchangeable, untouchable. People often think from the OS and below, transport layer, network layer, and link layer, things are hard to change. But no, I think starting from early 2000, there's a group of people in US pushing this very special technology called the software-defined networking. This is in the network layer. That's even below the transport layer. Okay, what it does is to try to set up these tunnels so that traffic can go through a specific way in a consistent way. So the way it works is a little bit like the virtual circuit we've talked about earlier in chapter 1. But I think it's going to be a lot more powerful, all right? But I think it's not going to work just like the circuit switch network, which everything is pretty much defined in hardware. Okay, we'll see more about SDN when we are in chapter, I think, 4 or 5. All right, and let's see. Team 4, okay, good. Kevin here is also providing his thoughts. If we want immediate response, I think you said, then UDP should be included. Yes, definitely. You will see also that some of the application services are actually implemented using UDP. Otherwise, TCP will be better. At least it guarantees reliability. So POP and RO could use a combination of UDP. Oh, that's a very interesting point. So you're saying that in a game, one could use TCP for certain communication and UDP for other communication. I see. Yeah, that's a good point. Yeah, so what I was saying that in this role-playing game, a lot of time the players are chatting and then trying to, conspire something and then talk about the strategies to counter a big mob, a big boss. Yeah, so the chatting part can probably go in reliable transfer, or the shopping, the online treasure part can go reliable. But hunting down the mob part could be, because it's, very strict, could be in UDP. Interesting. Or if this is players doing the real voice chat, then it could be going on UDP. As I learned yesterday, there's this score that you guys are using to communicate using real voice. in a game. Okay, cool. All right, so I guess that's the first part of the Q&As. Now let's move on. And we'll move on to this thing, PA3. So that you guys have the opportunity to interact with me just in case that you see problems that you want to ask. Oh, no problem, Kevin. It's not an issue at all right? So let's go ahead and start playing the PA3 videos. Oh, by the way, I'm just going to skip PA1 and PA2 because one is past due, but PA1 should be quite straightforward. PA2, now if you know one programming language already, then it's not that hard to learn the basic syntax of Golang. So PA2 during tomorrow again. I'll now walk through the videos, but PA3, starting from there, we'll be doing serious socket programming. So let's go through socket programming using Golang. So let's go. Okay, welcome to PA3's video walkthrough. This is part 1. From the programming assignments page, you'll see that PA3 is about upload client. So what I meant there is in your PA3.go, you'll be implementing a file upload client. Now, no worries. We'll be introducing you to a couple examples. So there are a pair of client and server programs. So through these programs, you'll see what are the APIs you could use to enable socket I/O access. Now, network sockets, just like screens and keyboards and files, there are also system I/Os. We'll take you through the examples momentarily. For now, let's finish the description here. Once you're done with the example, you'll be ready to PA3.go, which is a file upload client, which does step 1, step 2, 3, all the way to 7. One by one. In step number 1, you need to connect to the server that Poly has already implemented and set up running on the workstation at port 12,000. And then you'll prompt your user for the upload file name. Third, figure out a way to capture the file size first, and then send that particular value to the server. So make sure that you send just the value in a single line. Step 4, read the file and send the entire file's content to the server. At that moment, server will send you back a message. So your client program here needs to receive that message, print the message, close the connection that you have set up in step 1, and then terminate the program. So that's what's expected in PA3.go. In part 2, we'll start by going through the simple server in the program pair. This is video part 2. Let's start with the simple server first, and then we'll continue on to the simple client in the next video. So what the simple server does is to receive a string from the socket, which is connected to the client, prints on the screen, and then send back the size of the string to the socket, therefore reaching the client. So for now, let's start server 101.go. Type up this block of code into it. It's slightly longer than the examples we've seen earlier. Once you're done, replace your port in the program. So that is in the second line in the main function. So let's scroll back and see. Main function right here. Second line in the main function. There's indeed your port number bracket. So replace this with the port number you're assigned. How do you know what is the port number assigned to your team? Copy and paste this URL here. Okay, that should take you to a page like this. If you are team 12, use port number 12,012. If you are team 7, use port number 12,007. Now, once you're done with that, you may now execute the code. The behavior of the simple server is a bit unusual though. You'll see the server is started, but it will also look like it's hanging. The thing is that it's actually not. What it does is simply to wait for a client to connect. You'll see the simple server's action when we connect the simple client to it, which is coming up in the next example. For now, leave the server waiting and start another terminal so we can work on the next assignment. If you don't want to bother, just hit Ctrl+C to force quit simple server for now. So this is what it looks like. A command line, execute server 101.go. It prints something saying the server is launching, but it kind of hangs. It doesn't come back to the command prompt either, so it just wait infinitely. So this is what I'm saying here. Simply waiting for a client to connect, and we'll see in the next example. But the next video will be the code walkthrough. Let's learn the APIs so that you can write the client program. This is part 2. This is part 3 of PA3's video walkthrough. Now let's walk through server101.go. Let's do this on the editor because it looks prettier here. First line is package main. Yeah, this means we include all the basic APIs. And then we include 3 more sets of APIs. First 2 are format and buff.io, which we've already seen in PA2. The third is the package net. This is very important. This is also the package that we'll be importing for all the assignments in the rest of the semester. So what's defined there are all these socket.io APIs. Reading from socket, writing from socket, or more basically, opening sockets and closing sockets. Down here you're seeing the first line that looks new to you is exactly to open a socket. Net.listen here is to open a very special type of socket called the listener socket. So we specify what type of transport service we're going to give to this listener socket. We also specify the address of the listener socket. So A0, A3 here is the port number that I use temporarily for the demo purpose. And the listener socket, we are actually assigning it so that it runs over a TCP connection. This is a reliable data service that we'll talk about a little bit in Chapter 2, but a lot more in Chapter 3. Alright, so listener socket is a TCP connection running on port A083. The return values of net.listen are twofold. One is exactly the handle to the socket. So ln here is a variable of the connection type. Okay, so socket's handle is always the connection type, which is also defined in the net package. Second value is the error message. So we'll just ignore this for the interest of time. Now the second call that we see, ln.accept. This one here also creates a socket. Accept creates also a socket, but it's a data socket. Unlike the listener socket, listen creates. Okay. So ln.accept is a method of the connect type object. What it does is it waits for a connection request. So this is typically coming from a client. Okay. If there's one such connection request arriving, at port A0, A3, the listener socket calls the accept method and creating the data socket. So that is the value returned by the API, and we store in CONN another variable also of the connection type. Again, let's just underscore the error, ignore processing of the error. The next two lines, defer ln close, defer CONN close. These are to close the two sockets we created earlier. ln, the listener socket, CONN, the data socket. Now, defer is saying that we will be closing the sockets at the end of the program, which is down here, after the write flash. Yeah, because of course we cannot be closing the socket now because we are still to receive the string, right? And telling back the client what is the size of the string. Good. Next, buff.io new scanner. Cool, this is familiar, right? We have used this call before to wrap around the file handle so we could read. We can scan from the file. This time, we actually wrap the scanner around the data connection. And so that when we call scanner scan, we read from the data connection, which means we read from what the client is trying to send us. And we read it one line at a time. Scanner text here converts the byte stream into the text, therefore becoming a string. So message here is a string variable storing that message, that string the client sent us. And then we print the string here. Next, we wrap around the socket again with the writer. So writer is so that we could write something out, okay, onto the I/O. So writer here, we can call write string here, therefore writing a message out through the writer, which wraps around the data socket. As a result, the client will receive, okay, the string that we send them. Now, new line is the message we send out through the socket. And it is actually a result of doing this. Format dot sprintf. This is string printf. So what this API does is to print a string onto a string variable. So the output of this API is a string essentially. Now, how do we form the string? So double quote, just like printf, right? Inside the double quote, that is what we intend to print out. And this time, we take a value, and then followed by that, print bytes received, and then new line. And what is the value? It's the value here after the column. Len, parenthesis message. So message is what we have received from the client. So len is the API in the very basic package, the main package, that's taking the message and then find out the length of the message, and so that it's going to be filled here. So new line there will be taking the size of the message and then print size of the message bytes received. All right. Last is just writer.flash. This is to move the string that's still in the memory and then push it physically through the socket and eventually reaching the client. So this is video part 3. We'll move on to the simple client. By the way, I'm removing the camera headshot from the recording because my camera keeps freezing working with OBS. So let's just keep the video simple. All right, hello world client is how I call the simple client example. Because what it does is to send a text string, hello world, to the server. Server will send back a message, so this client 101 here will also be receiving a reply from the server and prints that. So let's go ahead and start the file, client101.go. copy the entire code block here, all the way down, and then replace your port number in the first line of the main function. Main function right here, and replace your port number here in the first line. So remove this and then type up your port number. So that is the port number assigned to your team. Just like what you did in server 101. Right? Now, before you try our client 101, start server 101 first. If you did force quit server 101 earlier, definitely do this. If you didn't, that's great. You can just go ahead and start another terminal and then run client101.go. What you will see next on the terminal screen is this: send a string of 13 bytes. Server replies, column, 12 bytes received. And then the program terminates, and then the control is back to the operating system. So you see the prompt. Now let's go back to the client101.go and walk through the code so we figure out why it prints these two lines. That'll be in the next video. Now you're ready to start implementing ep6.go, the file upload client, in which you need to make sure that it connects to the server. Now, this is a file upload server that Poly has pre-implemented and pre-installed. It's working on the workstation and right at the port number 12,000. So make sure that you change your ep6.go's dial-up address to the workstation's address and towards this port number. And then your program should prompt the user for the upload file name. First, you need to find out the file size of that file. Well, we did not talk about the APIs that allow you to grab the file size quickly. So you will have to exercise your creativity a bit, or see if you could use your detective ability a little bit to Google up if there are APIs available to allow you to get the file size quickly. Now, set the file size in a line like this. And then you may open the file and then extract file content and then send the entire file. All right. Now, some of you might need to go back to PA2 to review the APIs to access files. Now, once the server receives the entire file, it's going to send back a message. So your client there needs to be ready to receive the message right after sending the file. Now, if everything is okay, it needs to print the message. So tell what the server says. And then you may close the connection and terminate the program. So let's go to the demo mode and then try out the ep6.go, shall we? So let's go run. Oh, well, let's take a look at Poly's ep6 directory. So go to the ep6 directory. Let me show you the files I have here. All right, so I do have server 101, client 101 created for the exercising purpose. And then I've implemented my ep6.go. And yeah, these are the bytecode that I've compiled from my ep6.go. So, I mean, you don't have to do that. You could just simply do go run ep6.go. Now, this is my server that I put on the workstation for you guys. Is a file upload client to contact to. So, yeah, you won't be having these two files. All right, so let's give it a try. I've already pre-modified my ep6.go so that the IP address is exactly the workstation's IP address. And the port number is 12,000. So I do this and see if I connect to the server. There we go. That means the dial-up API is working. Therefore, the process goes to the next step, prompting the user for file name. Now, what do we want to upload here? Let's upload server 101. Okay, so go. Good. So client finding out the file size, and it's 560. Perfect. File size of server 101 is indeed 550. And then the client will be sending the entire file over and then receiving a message back from the server, which says 560 bytes received. So my server there is a bit smart, unlike what we see in server 101. It's returning the string without the new line symbol, as what the scan API for a scanner does. So I'm pending a 1 there, essentially. So you see that the server is responding something correctly. Good. So that's what you need to do to test your PA3.go. There's an alternative allowing you to be more confident that you've done the right thing for PA3.go, and that's coming up in the next video. To do the testing, you can try to do this alternatively. Compare your PA3.go's behavior to pollys PA3 bytecode. The poly has already precompiled her PA3.go, as you've seen in the previous video. And Poly has also put it up available over here at this URL. So log on to the workstation, download the bytecode. Now, the bytecode is going to work only on the workstation, unless you are also a Mac user and the architecture is identical to the workstation. Otherwise, it's not going to work. So the Windows bytecode is going to work on Windows machine architecture. Mac's bytecode is going to work on Mac's machine's hardware architecture. That's why you have to do this on the workstation. All right, so log on to the workstation and curl that file over. So it's a big file. So let me just copy the whole thing so that it's convenient when I'm doing the demo. Okay, yeah, direct it to a file called pollys PA3. And then change the permission. chmod is the OS command to change the file permissions. And change it this way, so the user has the executable right of this file. And then you may execute the file. Let's go to the terminal mode and let me demonstrate. So we're here. PA3 subdirectory of the home directory of user CN team 15. Let's curl the bytecode over. Don't forget to direct it to a separate file. It doesn't need to be pollys PA3. It can be anything else. All right, so now we have it. Yeah, if you don't do the directing to another file, then the bytecode is going to print on the screen. It's going to be messy and take a while. So yeah, make sure you have this redirection of the output of curl. Okay. So we should see a new file showing up in the directory. There we go. Yeah, now you have pollys PA3, but you don't have the executable permission. So let's change mode and add executable permission to the user, PA3, and then execute. There we go. It behaves just like when you do go run PA3.go, where you have your source code and you finish debugging and seeing it working. But in the process of programming and debugging, you might sometimes want to refer to how pollys PA3 works by executing this bytecode. So that's again the upload PA3.go here. There we go. It works exactly the same as go run PA3.go. That means, hey, if your PA3.go works exactly like the bytecode, then you're perfect. Okay? And that's the end of demoing testing of PA3.go. Let's go to the next video. Great. We're done with the testing. There's just one more thing I would like to mention. That is the package we're learning here. So net is very new, but it's very important. If you are going to do more socket programming, which is what you need to do the rest of the semester, then you might be referring to this documentation. So this page here, golang.org package net. In there, you will see a socket connection does have APIs allowing we to read or write to the socket. So read is to read from the socket. Write is to write into the socket. The way they work are very much like the scanner scan and the writer write string we've tried earlier in the examples. The limitation of the read is, however, unlike the scanner scan we used, we could actually specify that we read a line or read a word or read a byte at a time. But read here is going to read whatever space that you allocated, and it's going to read until it's the end of the socket. So not exactly that flexible. So often programmers goes to the buff IO as a resolve for using read or write. So that's all for PA3. Now enjoy. Ouch, ouch, ouch. No voice. Sorry, I muted. Yeah, and because you know what? I scrolled all the way back to the top and I didn't see you guys typing. So sorry about that. Yes, I kind of muted myself so that you don't hear me drinking water and all these other things. Oops. What should I do? Let's go back. Okay, we have a bit time, so sorry. Still a bit flaky here. Yeah, SDN. So it's one of the techniques, and it works somewhat like port forwarding, but it's not exactly port forwarding. Let me see if more typing up. Audio is muted again. Yeah. So maybe in the future I'll just not mute, and then I'll try to be quiet. That might be the better solution for this. Yeah. Is SDN like port forwarding? Because this is a very interesting question, and port forwarding is such that hey, for a traffic coming from a certain port and then you go to another certain port. Okay, we see this in this thing, NAT, the network address translator. If there's a certain traffic coming from a certain port and we map such that we send it out through another port, okay, that port number is actually the socket port number. All right, SDN there is very, very flexible. It can definitely do port forwarding. So it can check on the port number of the incoming traffic's original process. So in the packet, right, there's a source port number. So it checks port number and then it can decide which interface to forward the packet to. So that's one way to do it. But you see there, if this is going to be a router, okay, running SDN, then the router there will also have to look at the destination address. The thing with SDN is that it's actually even more flexible than this, than port forwarding. So it can look at the combination of destination address, the incoming port number, and the destination servers or destination processes port number. As well as maybe there's another tag saying that, hey, I do need this packet or this stream of data sending in higher priority. Okay, so SDN, way more flexible, way more powerful. It's something that's really cool that I see getting into the internet's core design these few years. Okay, again, that's coming up in chapter 4 and 5. Pay more attention when we're talking about SDN. Okay. And team 13 here is saying Farmville should be going through TCP as reliability is more important and timing not an issue. RO and PUBG, however, delay is a real big issue and probably the foremost issue, so UDP fits better. So that kind of agree with Team 4's solution, right? And defer, right? You can actually place any statement with defer at the front to any position in the program. It's going to put the line of the statement and at the end and execute at the end. Okay. And then, Team 7. Farmville TCP and PUBG UDP. But to provide better reliability for PUBG running on UDP, then you could do humming code. But the trade-off is that then you're sending more bits out. Therefore, there's a potential issue with the network bandwidth. All right. Is my camera freezing there? Okay, but hopefully you can still hear me. For RO. Team 7 thinks that TCP will be okay because RO is more a casual game. Most of the time you're just doing it in slow pace, maybe except when you're combating. So that maybe you can go to a net cafe and then have very, very good internet access. So delay is less an issue there. All right. So let's call it a day and come back next Wednesday. We'll talk about the rest of 2.1. The secure transport layer service. Okay, so TCP, UDP, does not provide security guarantee. So we'll hear about it next week. All right, so let me see, where do I click to stop here? All right, end stream.